Chapter 7, DiffEq, differential equations. Yes, that's right. Us nerds say DiffEq. And mathematical modeling. That's just differential equations. I don't know why they throw math modeling in there. I do know why they throw it in there, but everything we do should be math modeling. So I found my quote: show me someone who has done something worthwhile, and I'll show you someone who has overcome adversity. By, the college coach when I was in college football coach when I was in college, Lou Holt. And the point I'm making is you're in for some challenging times from this unit on. Yeah, I mean, there's a couple lessons here and there that aren't too challenging, but it's really puzzling stuff. They turn problems inside out. There's so many different techniques for integration. Differentiation is just follow these steps. Oh, it's an exponential, do this. Oh, it's a logarithm, do this. Oh, it's two functions being multiplied, do this. Now you get into integration, which is, they call it differential equations, meaning dy dx equals something. So therefore y equals something by integration. And there's a lot. So when you're done here, you're going to understand how to integrate differential equations, slope fields, Euler's, not Euler, Euler's method, more integration, they call it anti-differentiation, using the technique of substitution, parts, and then how to handle trig and log functions, which are just doing the opposite of what we did in differentiation, but it's just confusing because your brain has learned to see things one way. Now you have to train it to see things the other way. We'll get into indefinite and definite integrals, which is easy. You've already done them both. And you'll understand Leibniz notation, which is dy dx. We've already done that too. Separable differential equations. Nobody gets that. It's not hard. It's really very, very straightforward. But people get so bogged down with so many different types of integration that when I throw a very simple separable differential, it just means put the y's and dy's on one side and the x's and dx's on the other. They just get lost. It occurs to me I didn't do this. So this is tricky. This is doable. I don't remember what my quotes are. I'll just run with these as best I can. I know Euler's method, how to apply it. Tricky, but doable. Anti-differentiation by substitution, hard. By parts is actually easy, but everybody considers it evil. And trig log is just tricky. Separable is just so confusing. People have just kind of checked out by this point. Leibniz notation is easy. Red pen is running out of ink. I'll get a new one in a minute. There we go. Exponential growth and decay problems. That's not too bad. Newton's law of cooling. Tricky. Not essential. It's just saying if there's something's hot and there's a lot of it, it takes a while to cool down. The less there is of it, the faster it cools down. Or the slower it cools down. The rate of growth slows down, whatever. This is important. Understanding logistic growth. There's always 1 to 2 questions on there. And this is evil. I actually don't have any problem with it, but most of my students consider it pure evil. So let's dive in. So we're going to get into slope fields in a little bit. Conceptually, you look at it and go, there's no way I'll ever understand that. And then we do it and you're like, oh, really, it wasn't that bad. What was the big deal? So what's a differential equation? Well, here's one. It's got a dy dx in it. That's it. Now, this is a first order, but we never get into that. These are all the ones we do. It could be d squared, y dx squared. It's not. So now they're saying, all right, use anti-differentiation and find a y equals. Well, the way we would do that, we would say, take the integral with respect to x on both sides. Well, the integral with respect to x just gives you y. I've had a problem here in the past. People, well, I don't get it. Why does it do that? That's a definition. There's nothing to understand or explain. To go backwards, we use this operation called the integral. We do an antiderivative when we see an integral with respect to x. But I don't get it. There's nothing to get. all right? If you took the derivative of this, you'd get dy dx. Yeah, I know, I get that. Well, why do you get that? It's the same thing. It's just a rule I gave you. To go backwards, we take the integral with respect to x and we get y. That's just the way it works. Technically, I think what we would actually say is multiply both sides by dx. And we get a dx up here, take the integral of both sides, and it really would be something like this. Integral with respect to y, integral with respect to secant squared x plus 2x plus 5 dx. So that's really what we're doing. Integral with respect to y, integral with respect to x. This is easy. Y, derivative of y with respect to y is dy. Over here, a little trickier, but you should know, oh yeah, that's right. If I have tangent of x, or tangent secant x squared, plus 2x, add 1 to the exponent next to the first, add 1, 2, and divide by 2. Add 1, 2, and divide by 2. And then check it. Derivative of x squared is 2x plus 5x plus this constant c sitting out there annoying you. Now we've got a lot of problems here. How do we find c? Well, we give you an initial condition for the next one we're going to do. Okay, well, what if we don't? What if we give us this weird other stuff? I'll show you how to do that. And it bothers people because I can do it fairly quickly and easily because I finally figured out the model in my head that works. A lot of people can't get there, and I do my best to show them. It's really not that hard. We'll get there. Now, do we actually write in all that nonsense? dy dx equals e to the x minus 6x squared. No, usually we just jump. Y equals e to the x minus 6x, add 1 to the third over 3. Check. Derivative of e to the x is e to the x. Derivative of x to the third, 2x to the third, 3 up front, 6x squared. Check. Minus. Then we put a plus c. And here's where we put that initial point in. X, y. 0 equals e to the first minus 2 times 1 to the third. Interesting. I did this in a very different way. Wish I'd left myself enough space. I could have done it again. Oh well. Plus c. C equals, going to swing that over. 2 minus e. Minus e plus 2. Interesting. I think we'd like to put the e first. It doesn't really matter. So we get y equals, yeah, I'll do this problem down here the other way. Y equals e to the x minus 2x to the third minus e plus 2. I would check it every single time. dy dx equals e to the x minus 6x squared minus 0, plug in 1, minus 2 and 2 cancel, 1, e minus e cancels, I get 0. Check. So here's another way to do this. And this is the model I talked about earlier. When I see this 0, 3, I immediately rewrite this problem as y equals integral. So they give me the x, 0 to x. I have not done any calculus. 2x minus secant squared x plus 3. This way works. This way works. I won't have a plus c now. This is an indefinite integral problem all the way up here. There's no limits, so I just put plus c. I can do it with no limits, so we basically threw this in here, threw this in here. All right, notice the dx's cancel if I just left it like that instead of multiplying it out. All right, and get a plus c and fill it in. Or I can do a definite integral where I put the limits. And you say, but that you lost me. 0, 3. You just always put a 0 here and a 3 there. Here's the model in my head. Plug in 0. Integral from 0 to 0 is 0. Should get out 3. This is pretty handy. I recommend it highly. Most students don't listen to me. What else is new? But I really recommend it. So here we go. 2x squared over 2x squared. Oh no, you shortcutted it. Yeah, we'll just check. Derivative, yeah, good. Minus tangent of x. Hey, didn't we just do this problem? Sure looks like it. Not quite. Similar, but different. Okay, and build the wall. 0 to x plus 3. Y equals, plugging in x, we really should have a dummy variable, t dt. Then x goes in with t and t. Who cares? X squared minus tangent of x minus 0 minus 0. Tangent of 0 is 0. Plus 3. Y equals, that's going to be x squared minus tangent of x minus 0 plus 3. X squared minus tangent of x plus 3. Now, technically, I have to say it's from negative pi over 2 to 0 to pi over 2 because it doesn't work everywhere. Doesn't matter. We're not getting into that. I hope that made some sense because off we go. Here it is again. Find a solution to the differential equation. F of 7 equals 3. Want to do it with a c value? Want to do it this way? I don't care. I have to write the point x comma y, 7 comma 3. My brain just works that way. Well, f of x, I was going to say y, and it's not that big a deal if you mix and match them, equals integral from 7 to x e to the negative x squared dx plus 3. Oh no, we're done. How the heck would I know we're done? How come we don't go do the antiderivative thing? I happen to know from practice, we can't find the antiderivative to this because the chain rule is going to cause problems. So if somebody says, okay, fine, well, what's f of 4? Well, now we have a model and I can put it in my calculator and int it. And that's it. That's it. It just bothers people to no end. Graph the family function, solve this differential equation. Y equals integral, no values here, cosine of x, dx, yes, you need to put the dx, y equals sine of x plus c. So we're going to get into slope fields here, all right? So sine of x, I will do the first one, 1, 2, 3, 4, 2 pi, pi over 2, 3 pi over 2, and 1, 1. I'm going to put the first one in as a solid line. After that, we're going to get away from it. Slope fields mean, what's the slope at that point? So we would actually do this. Well, here it's 0, here it's 0. I know I missed the dot. Here it's -1, here it's +1, here it's +1. And we could put in more. Now, if there's a plus c, let's assume everything had 1 added to it, or half, because I don't feel like going all the way up there. You'd get something like this. I feel like putting in this and this out here. And I feel like putting in this and this out here. That is what a slope field is. Since you have plus c, you go anywhere. You could also go down. And you get these patterns. They aren't always the same in a vertical column. They are in this particular case, but generally not always. So that's a slope field. So we went back and we drew in the slope fields. If you want to see this, go to Desmos and Google, or Google Desmos slope fields app, and then you can see this. Your calculator can do stuff, but you have to download a program. A lot of people get real jittery. Oh, I gotta have the program. I don't know what's going on. I gotta have the program. No, actually you don't. I printed them out for you. All right. So let's try it again for x plus y. And you're probably like, oh no, there's x's and y's on the right side. Doesn't that cause problems? Well, let's find out. Personally, I don't think it's that big a deal, but hey, what do I know? So this is a AP problem. Pretty rare. I've only seen it once. One, two, 1, 2. Okay. So here's how it works. Plug in a bunch of values, -1, -1, -1. I put in 2s, but we're not going to go that far. We're only going to go up to 1s. So -1, 0, 1. 0, 0, 0, 1, 1, 1, 1, 0, 1, 1, 0, 1. What the heck's going on? Well, let's find out what the slope is at that point. That's all we did on the previous page. We put in little lines that indicate the slope at that point. So now we got this like little trick where we can say, all right, let's go. -1 plus -1 is -2. Hold that thought, I'll come back to that. -1 plus 0 is -1. -1 plus 1 is 0. So at -1, 1, slope is 0. Put a little horizontal line. At -1, 0, the slope is -1. Up to the right is positive. Sorry, I just realized I have to change colors here. Down to the right is negative. The reason I held off on this is now we have to make it a little bit steeper than that. So at -1, -1, we get slightly steeper. It wasn't that steep. That'll have to do. At 0, 0, oh no, we have to fill these in. So we're just adding them together. -1, 0, 1, 0, 1, 2. 0, -1, -1, 0, 0, 0, 0, 1, 1, 1, -1, 0. Notice the horizontal lines on the diagonal. I told you they don't always match up top to bottom. 1, 0, 1, and then here steeper. That's a slope field. Let's go out here, 2, 0. 2 plus 0 is 2. 2 plus 1 is 3, even steeper. 2 plus -1 is 1. 2 plus -2 is 0. 1 plus -2 is -1. Seems like they always go out a diagonal here. Seems like they always go on a diagonal here. Let's see, -1, -2, -3, that sort of thing. That's a slope field. You can actually kind of follow the curve. They ask you to do this every now and then. It's not as big a deal as you think it is. You can actually follow the curve. But hey, you go ahead and match them up. How do you do it? I'm leaving that to you. I'm certainly not telling you. I would pause this and I'm going to put the answers in right away. Okay, so for first one, x minus y, whenever these numbers are equal, we get a 0. So all of these on the 45s will be 0, 0, 0. no, no, no. So this is B. Now this one, whenever we have a 0, we get a 0, so we get a horizontal line. So we should have flat lines. Here's flat lines. Here's flat lines, but also we should have flat lines here. This or this, and here's flat lines. You can't see them; they blend into this. I got this off of Desmos. So flat lines, flat lines, flat lines. Darn, they're both the same. So I don't know which one it is. So if we had 1 and 1, have 45. Yeah, that's 45. 1 and 1. That's also 45. It's very unhelpful. Are these tick marks? No, they're not. These are horizontals. Let's say, am I reading this wrong? Let's try 2, 1 and see what happens. 2 times 1 should give me 2. Nice steady, it does. 2 times 1 gives me the same thing. Where the heck are these different? Down here in the first quadrant. Okay, cool. So 1, -1 should give me -1 if I'm multiplying them. 1, -1 also gives me -1. It's getting a bit upsetting. Well, these are vertical lines in here, even though they don't show up here. No, not necessarily. Horizontal, vertical. Oh, wait, I totally messed up on the 2 times 2 is 2. Yeah, it gets steeper as we get closer to 2. So I believe this one is C. We'll see how I did. Woo, a roll. Now that's over Y. Whenever the Y is 0, we get a vertical line. So Y is 0 here. We get vertical lines. Those are vertical lines. This doesn't show and this doesn't show. These are getting closer and closer to half. So I'm going to go with D for this one. Meaning the last one is A, but it makes sense. If X is 0, we get vertical lines. Look at what's on either side, we get vertical lines. Whatever. That's pretty hideous, I agree. So that's it. That's pretty much all you're gonna have to do on the slope fields on an AP test. All right. So how do we march along a slope field? I mean, we can just look at it and say, well, if I give me a point here, it looks like the curve would do something like this. Give me a point here, curve would go straight down. Give me a point here, curve would kind of go straight up. So I'm going to show you something. You're not going to understand it at all, but it's using the concept of linearization to get along the slope field. I'm just going to jump right in. And I'm doing this one pretty ice cold, so we'll see how it goes. We use a bunch of increments here. On an AP test, they only use a handful because there's only so much time. So we start with our XY. And then we go with our dy dx, similar to how we built the slope fields. Right, x plus y. First point is 2, 0. Then when we get up to 3, so all the way down here, I'll have 3, something. And then when we go up by 0.2s. By the way, when you see this on an AP test, the answer key will have done it differently. This is delta y here, and I'll show you how we get that in a minute. And here is your new xy, which is going to end up over here, right here. So we do it, we march along the slope curve here, do it again, so on and so on. I can already tell you the x because the x's go by 0.2s, 0.2, 0.2, 0.2. This will be 2.2. This will be 2.4. This will be 2.6. This will be 2.8. 0.2, 0.2, and we're done. We don't actually go into the last column. So dy dx, 2 plus 0, 2 plus 0, 2. Now delta y is like dy dx times delta x. These are close. Smaller we make this, closer they are. In this case, we'll say close enough. We cross them out, we're left with the dy. 2 times 0.2 is 0.4. 2 plus 0.2, 2.2. 0 plus 0.4, 0.4. We are marching along the slope curve. dy dx, how do we get this? 2 plus 0 because of this. 2.2 plus 0.4 is 2.6. 2.6 times 0.2 is 0.52. 2.2 plus 0.2, 2.4. Where was I? 0.4 plus 0.52, 0.92. 0.92. Add them together, 3.32. Multiplying by 0.2, 0.664. Add them, 2.6. Yes, I need a calculator for this, 1.584. 2.6, 1.584. dy dx, add them, 4.184. Multiply them, 0.8368. Add them, 2.8, comma, 2.4208. 2.8, 2.4208. Add them, 5.2208. Multiply 1.04416. Add them, 3.0, 3.46496, 3.46496. I'm not going to do this. There's our answer. F of 3 is approximately 3.465. What a pain. However, just to be clear, you would not actually have that many steps. The most I've seen on a test is 2. You'd be done here. They don't want you to have to go crazy with this. Now that was going forwards. We could also go backwards. They never asked us on a test. So let's just set it up and start it and then be done with it. It's good practice. X comma y. Start at 3, 2, and then what's going on at 1.5? So this is delta x. No, this is dy dx. Sometimes I mix up my delta x and dy dx. And it's 2x minus y. So the first point is 2 comma 3. 2 times 2 is 4, minus 3 is 1. And then your delta x would be negative 0.1. Multiply 2 to get your delta y. And that is a 2.9. And then your new x comma y would be, oh, silly. Where did I get 2.9 from? That is very weird. 1 times negative 0.1 is negative 0.1. So you would get 1.9, 2.9. Next line, 1.9, 2.9. dy dx until you get down to 1.5, right? So I actually did all this. And when you get down to 1.5, you get 1.5, comma, 2.611. And how is that connected to the slope field? The point we started at was 2 comma 3. 1, 2, 3. And we go to 1.5. 1.5, we got 2.6. It's upsetting. 1.5, and we got about 2.6 about here. So we were just marching along the slope curve. If we kept going, it looks like it would do something like that. Again, I've seen this on an AP problem. They ask you to kind of draw the graph in. And this point here, 1.5, 2.611. Warned you, tough stuff. Good luck and happy mathing.